Hi, and welcome to the Foundations course Lesson 6 on describing and testing relationships. In Lesson 5, we looked at how to test for differences between variables, but in this lesson, we're looking at how to describe and test for relationships between two variables. And we will start off with association, and then we'll continue into simple linear regression and correlation, and we'll end the lesson on agreement and reliability. So let's start with association. What is an association? Well, it's nothing more than a relationship between variables, and it's not necessarily causal, but we can use between patient differences in a variable, for example, like the one depicted in blue here, variable 1, to predict differences in variable 2, at least to a certain degree. But notice that I said you can predict differences in a variable and not explain or cause differences in another variable. And that is why association does not equal causation. You probably heard this phrase before, but it's a very important distinction. We will do a deep dive into this subject in the later lessons where we will discuss the different study designs in medical research in detail. And you will come to learn that there are only certain study designs that are suitable for demonstrating a cause and effect relationship, whereas the other types of research are merely prediction research, and so you can only demonstrate associations. But for now, let's keep it more simple. And we can ask ourselves a question to determine whether something might be causally related. And that question is, if I change variable 1, would it be reasonable to expect that variable 2 might also change? If that's the case, then that might signify a causal relationship. Whereas in association, such a change is not expected, because there is no cause and effect pathway between these variables. And there are multiple other reasons why association and causation are not equal. For example, if we want to explain differences in variable 2 between patients through observed differences in variable 1, then that prediction oftentimes goes through multiple layers of other variables, and some of them we might not even be aware of or have measured in our study. And we oftentimes think that we know the direction of the relationship. For example, in this case, we think we're predicting variable 2 from variable 1, but in reality, it might be the other way around. And for prediction research, it doesn't really matter, but in cause and effect relationship, this would be a big problem. The terms association and correlation are often interchangeably used, but that's not correct from a statistical point of view. There are different types of associations depending on the types of variables that are studied. For example, associations between two categorical variables, or a continuous and categorical variable, or two continuous variables. And only the latter type of association may be called a correlation. And that is because correlation is closely linked to linear regression. And we are going to look at what that actually means right now. So a correlation is an association of two continuous variables. In linear regression, we estimate how we can best predict the outcome variable, which we give the letter y, as a mathematical function of the explanatory variable, which we give the letter x. And in simple linear regression, we only have one explanatory variable, whether in multiple linear regression, we use multiple explanatory variables. And the correlation coefficient tells us something about the strength of the association between the two continuous variables. Let's take a look at how simple linear regression works. And we'll do this by exploring this scatter plot that might be familiar to you. On the x-axis, we represent different x values of the explanatory variable, whereas on the y-axis, we represent different y values of the outcome variable. And all the scatters here are values of observations in our cohort. So it means that, for example, here at x is 10, we have an observation with outcome is 10. And here at x is 25, we have an observation of y is 20 or slightly more than 20. And so we pair all the y and x values that we have observed in our study and we plot them in this graph. But of course, in our cohort, we know exactly what all the observations are. What we are interested in is whether we can construct a general formula with which we can predict outcome variables that we haven't observed in our study as a function of the explanatory variable. And we do that with a regression equation. And that regression equation has a regression line as depicted here. And that line graphically shows us how the regression equation works. The equation has the general formula y is beta 0 plus beta 1 times x, where beta 0 is the intercept or offset. And we can find it in this graph by looking at the y value for x is 0. And that's the point where the line intersects the y-axis. And beta 1 is the regression coefficient, or the slope of the regression line. And we can find that by looking at the difference in y values for observations with different x values. And then we divide delta y by delta x, and that gives us beta 1. I want you to note that only if all observations in the scatter plot are perfectly aligned on a straight line, then the regression line and its associated beta 0 and beta 1 are unambiguous and very simple to define. In medical research, that's hardly ever the case. So usually we have to find the regression formula or line that fits best to the data. But that means that there are multiple options, and there's always some error remaining in that estimation. And remember the residuals from the lesson where we explain how to determine a standard deviation, that are the bars represented in the graph here. Those are the errors that remain. So in simple linear regression, we want to minimize the sum of the squared residuals, or the difference between the observed values and the predicted values as a function of the linear regression equation. And statistical software will find the formula with the minimized sum of the squared residuals. But let's look at how to calculate it if you were to do this manually. These are the formulas that you would need. But don't try to remember them. So for beta 0, we would take the sample mean value of y and then subtract beta 1 times the sample mean value of x. And for beta 1, we would start with the product of the differences between the sample mean x values and the observed x values, and the sample mean y values and the observed y values, and then sum them all up for all the observations. And we would divide it by the sum of squared residuals of x values. And of course there are standard errors here as well as a standard deviation that you can calculate for the simple linear regression. You probably will never do this by hand, and you will use statistical software to do it for you. So to conclude this section about simple linear regression, we construct a linear function that allows us to estimate the continuous outcome variable y through the value of the continuous explanatory variable x. And we use the formula y is beta 0 plus beta 1 times x. And then we can also add the error function for the residuals, because the observed values never perfectly co-align with the predicted values as calculated through the linear regression equation. and we assume that these residual terms are normally distributed so that some of the observed values will fall above the linear regression line and some of them will fall below it. As I've said, we can use the correlation coefficient as an expression of the strength of the association between two continuous variables. And we usually use the Pearson's correlation coefficient, and you can calculate it by hand with the following formula, or you can use statistical software to do it for you. The more important thing is the interpretation. It has a range of -1 to +1, where 0 means there is no correlation at all, -1 means there's a perfect negative correlation, and +1 means there's a perfect positive correlation. But note that the correlation coefficient tells us something about the strength and the direction of the correlation, but not its relevance. So you still need to think about the clinical relevance yourself. And furthermore, many authors also use a p-value to state whether the correlation coefficient is significantly different from 0, but I don't think that's a very relevant statement. You're better off just showing the correlation coefficient and maybe an associated 95% confidence interval to state the uncertainty of your estimation of the correlation coefficient. The R-squared is a related concept and it can be calculated by the correlation coefficient squared. And it's the percentage of variability in the outcome variable explained by the explanatory variable. So for example, an R-squared of 0.60 means that 60% of the variability in Y can be explained by X. It's a more intuitive measure for the strength of correlation, but it doesn't tell us anything about the direction. So if you give an R-squared, it's best to also depict the correlation coefficient. Alright, that's it for simple linear regression and correlation. Let's move on to agreement and reliability. So sometimes we don't want to know whether we can predict variable y through x, but we want to know instead how similar variable x1 and x2 are. And that is a question that relates to reproducibility, which itself relates to measurement error. And reproducibility is an important part of diagnostic research in the field of medicine. So usually we want to know whether two repeated measurements at two different time points with the same method or performed by the same observer result in equal measurements. And that is called intra-observer or within-observer reproducibility. In other situations, we also want to know whether two measurements performed at the same time by two different methods or observers result in equal measurements. And that is called inter-observer or between-observer reproducibility. And reproducibility itself is actually an umbrella term for agreement and reliability. And unfortunately, these two terms are often used interchangeably in the literature, but they actually refer to two distinctively different statistical terms. Let's look at what that difference is. In agreement, we want to know how close scores for repeated measurements are to each other. So that's a measure of evaluation. Whereas in reliability, we want to know how well patients can be distinguished from each other despite measurement error. So it's a measure of discrimination. And in statistical terms, we can look at agreement with a count of equal measurements, that is called specific proportion of agreement. And we can look at the average discrepancy in measurements with something called the Bland-Altman plot. For reliability, we can look at the number of agreed measurements adjusted for chance with the kappa statistics. And we can look at the between individual variation as a proportion of the total variation with the interclass correlation. And which measure to use depends on the types of variables that are studied. So when studying categorical variables, And looking at agreement, we want to use specific proportion of agreement. And for reliability in categorical variables, we want to use the kappa statistics. But for continuous variables, we use the Bland-Altman plot with bias and limits of agreement in continuous variables. And we will use interclass correlation as a measure of reliability for continuous variables. All right, agreement. So let's start with looking at this table where we have depicted the outcomes of method 1 with a positive test outcome and a negative test outcome. And then the same for method 2 with a positive outcome here and a negative outcome here. And then we have the all familiar A, B, C, and D values. And A and D are the cases of agreement, and B and C are the cases of disagreement. So we can calculate a general proportion of agreement by dividing the number of agreed cases, A plus D, by the total number of cases. But we can also calculate positive and negative specific proportions of agreement. For positive, we take 2 times the number of agreed positive cases and divide it by 2 times the number of cases with a positive score. And that is, in this situation, 2A divided by 2A plus B plus C. So all the scores except for D because it has no positive score. And for the negative specific proportion of agreement, we take 2 times the number of agreed negative cases and divide it by 2 times the number of cases with a negative score. So all the scores except for A. And kappa statistic is, as we've already said, the proportion of agreement adjusted for chance variability. And we can calculate the Cohen's kappa coefficient by taking the difference between the observed agreement and the expected agreement as a proportion of 1 minus the expected agreement. And it can be calculated manually as follows. But note that this is a simple measure of kappa that is good for 2 categorical variables. But when you're using ordinal data, so ranked data, you may need to use a weighted kappa or a matrix of kappa coefficients. But we'll not dive into that as of yet. So now that we've discussed the agreement and reliability measures for categorical variables, we're moving on to continuous variables. In the Bland-Altman plot, we try to get an idea about the average difference between 2 continuous variables and the range of the differences. The Bland-Altman plot is a sort of scatter plot for the paired observations of 2 different measurements. But instead of just plotting the 2 measurements against each other, we take the mean of both measurements on the x-axis and the difference of the 2 measurements on the y-axis. And then we first look at the distribution of the scatter dots in the graph. If they're all over the place, then that means that there's a big difference between the 2 measurements. But if they tend to lie closer to each other on a straight line, then that means that they're pretty close. But how close? Well, first we will look at the average difference between the 2 measurements. And in terms of the Bland-Altman plot, we call that the bias. And it's depicted by this line over here. And in this example, we would conclude that there is an average difference of 5 between measurement 1 and measurement 2. And to be more precise, we can say that measurement 1 is on average 5 points higher than measurement 2. So that also tells you that it is important to think about which measurement you want to test against the other. So if we would put measurement 2 minus measurement 1 on the y-axis, we would get a value of -5. And then the second thing to look at are the 95% limits of agreement, which are plotted at minus 1.96 times the standard deviation and plus 1.96 times the standard deviation from the average. And what you need to do here with the 95% limits of agreement is look at how wide they are. In this example, they range from -5 to 15. So although our best estimate of the difference between measurement 1 and 2 from this sample is +5, a plausible explanation of the difference in the population can actually be found at all values between -5 and 15. And whether that is acceptable depends on the clinical context. So that's a call that you have to make with your clinical reasoning. And it's up to you to say whether you think the agreement between these two continuous variables is good enough or not. And the last thing to note in the Blind-Altman plot is whether you see certain patterns in the distribution of the scatter dots. What you can sometimes see is that there is some sort of funnel shape in the distribution where the differences between the measurements are larger at either lower or higher mean values. And that tells you something about systematic errors of the measurements. So it is definitely something to note. Last but not least, the interclass correlation coefficient, the reliability measure for continuous variables. And the abbreviation is ICC. So there are different types of interclass correlations, and it's best that you specify which type of ICC you use in your research along with the mathematical equation to derive it. The general formula is that of the between-subject variability, which you may interpret as the real variability observed, divided by the total variability, which is the sum of the between-subject variability and the within-subject variability. And the within-subject variability is an error factor. And that's pretty logical because the subjects do not change between two repeated measurements. So every variability between those two measurements must be some kind of measurement error. And we call that the residuals. We use variance for variability in the ICC calculation, and this is the formula for the standard ICC, which is called the consistency ICC, where we divide the variance between subjects by the total variance, which constitutes of the components variance between subjects plus variance residual. But there's another ICC, which is called the agreement, where we include in the total variance the term for the inter-observer variability or variance. And that one is only used in studies where you also compare the inter-observer reliability. I know it's pretty confusing that they call this agreement, but it's just something that has been adopted in the literature. Now, these variance terms can be estimated with an ANOVA analysis. And the range of values are between 0, where we have no possibility of discrimination because the entire variability observed is measurement error. And 1 means that there's a perfect discrimination, where the entire variability is real between subject variability. And an ICC above 0.7 is considered a good measure of reliability. Now we can also calculate standard errors for these terms, and we call them standard error of measurement. And for the consistency, it's just the square root of the residual variance, and for the agreement, it is the square root of the inter-observer and residual variance. Awesome, that's another finished lesson on describing and testing relationships. You're becoming quite the expert on medical statistics. And we have now covered the very basics of medical statistics, and in the next lesson we will extend this knowledge with a deeper dive into modeling, and after that we will look into the different types of study designs and we will learn what's important in those different designs.